Hello, everyone. On behalf of Cyberminder, I welcome you all to today's webinar on Real World Vulnerabilities Insights from Public Pentest Reports. A quick introduction to Cyberminder. Cyberminder is an automated and continuous attack path and threat exposure discovery platform. Our proactive approach helps organizations continuously monitor and manage their external attack surface, significantly reducing exposure to potential cyber threats. Moving on to today's session, we are thrilled to have Abraham Aranguren with us. He will be sharing his expertise on how to uncover real world vulnerabilities revealed in public penetration testing reports. With 24 years in IT and 17 years in IT security, Abraham leads 7A Security as its CEO. He is a passionate security professional with extensive expertise in mobile, web application, and web server penetration testing. Formerly a lead framework developer, Abraham is now a recognized trainer, co-authoring 7A Security's mobile, web, and desktop app security courses. He regularly delivers training at prestigious events including Black Hat USA, OAPS Global AppSec, and several others worldwide.
Hello, thank you, Naisa, for the introduction. So, hello, everybody. Thank you for coming. Yeah, today let's talk about this Cybermander webinar talking about interesting vulnerabilities from public pentest reports to give you like some ideas in your pen testing and similar, right? So let's go through this, right? So the who am I has already kind of been covered, and then we will be talking about mobile application vulnerability examples, web application vulnerability examples. Then we'll see some cloud and VPN, and then I can also show you an Electron remote code execution through prototype pollution demo if I have enough time at the end. So let's see. Okay, so I'm the CEO of 7 Security, co-author of all our courses, like the mobile, the web, and the desktop application security courses. Yeah, I've, being delivered training at multiple security conferences such as Black Hat USA, Hacking the Box, Cobas Global AppSec, and many others. Well, from this, you can, I was a developer first, and then I switched to security. So no matter if you are a developer or a security professional, I have your back, right? So I understand the pressure of developers to, I don't care how you do it, but it has to be working in production on Friday, as well as the frustration of security professionals when their concerns are not being addressed, right? So what we will be talking about today is the value of public pentest reports. And I'll just show you some examples, but there's like a lot more in our website. Now, this is all completely free. You don't need to register or anything. You just go to 70security.com publications and you click and you download the PDF directly. Now, this year, we've already done a bunch of audits, but a lot of them, they are not public yet, right? So we audited 100%, the Tor project, Amnesia VPN, Free Browser, WeNet, and the Sino browser, and DCOMS is also coming soon. So all these are not public yet, but several of these we hope will be public in the next few months. Of course, reports only become public after everything has been patched, right? Because we want to make the world a safer place, right? So there's a few Linux Foundation projects like Linux Chaos Linker from the previous page. We also audited OpenTelemetry, Logback. You might recall the Log4Shell vulnerability a while back. So these are all interesting, audits. We also audited the Tor project in 2024. This one is already public. On Amnesia VPN, we have audited several times. So we're just waiting for the okay to release the third audit that we did this year, which is not public yet. But the idea basically is you can go here and just download any pentest report and for free, right? You don't have to pay anything. You don't have even to register. You get the PDF and you can review real findings from real auditors in real applications, right? In many of these cases, the applications, especially for the public pentest reports, tend to be public, like open source software that a lot of people use, or open source software that is supposed to protect people in, let's say, difficult countries like China, Russia, Iran, and so on, like journalists, human rights activists, and people like that, right? This is to that 2024, 2023, and so on. There's also some pentest reports for 2022, and all that is there in Internet Security publications, right? So a couple of other interesting things that you can like search on YouTube to read more about is the Smart Sheriff application that was kind of mandated in South Korea. So it was so bad that we gave a talk about it. You can search for Smart Sheriff Dam idea on YouTube, and you will see like a few recorded talks about that, and also like Chinese police, and like Chinese police and cloud pets was the name of the talk. So these also covers a bit of the insecurity of Chinese police applications, as well as some like IoT applications like cloud pet, right? When you have like a toy that has microphone, camera, and so on, there's risks for that could put children at risk, right? So you can see those like on YouTube. So let's see now some mobile application vulnerability examples. So the first one I'm going to show is like task hijacking, which is an often forgotten about attack vector against mobile applications. Still works because Android only patched it in Android 12, so most applications have like a minimum Android version of Android 6 or so. So there's a high percentage of the user base still using outdated Android phones, so this attack still works. And basically, this attack works like this, right? So what we're attacking here is the task manager in Android, right? So we need certain attack requirements. Fortunately for the attacker, these settings are all pretty common and tend to be on by default. So most applications are vulnerable to this by default, right? So let's see how it works, right? So the way to find this would be you look at the Android manifest of the Android application, look for a launch mode of single task on the launcher activity, right? So if you have that, pretty much it's going to be vulnerable. And I'll explain the mitigation later on, right? So because this attack is a little bit weird, I think it'll make more sense if I show you like a demo. This was against the LeaveHomeSafe application, which was kind of a COVID-19 contact tracing application mandated in Hong Kong, right? So let's see how this works, right? So first, so this played already once. Now I'm playing the demo again. So first you open the victim application. Now this is the login page. For example, like the user tries to log in or whatever. But the idea is like now that you launch the application, this application is going to be in the task manager in Android, right? So you can see this is the task manager in Android when you see the open apps. And you can see that the LeaveHomeSafe application, which was vulnerable to this, is there, right? And then you have a malicious application on the same device, which we are simulating with this attacker app. And when we clicked on it, it seemingly didn't do anything, but in reality, what it did is it messed with the task manager in Android. So now, when you click on the target application, instead of opening the target application, the LeaveHomeSafe application, you're opening the attacker application, right? Now, this is just for demonstration purposes, so it's not so pretty, but in a real attack, this would be like looking exactly like the legitimate application, like the login page, everything, it would be completely undistinguishable for a victim user from the real application. And then you can capture the user credentials, right? And the second factor and everything else, because the malicious app can forward anything to the target server, right? And then you impersonate the user, right? So this type of attack is very common against banking applications, for example. It has been used many times against banking applications for obvious reasons, right? It gives like criminals access to the credentials, the bank accounts, and so on, right? This is how the task hijacking attack works. So so how do you fix this, right? So in the application tag, you should if you have a task affinity of an empty string, then the attacker has no can basically not do this, right? Because there's no affinity to target. And then another mitigation would be to change the launch mode to single instance, right? So if you do it this way, then the attack would be mitigated and this would no longer be possible, right? Something going on in the chat in between. Okay, so can you hear me well? Yeah, it seems like my
Yes,
audio is breaking a bit.
yes, now it's clear.
Okay, cool. Cool. So yeah, so this would be the way to awesome. Cool. So this will be the way to mitigate that. And then another problem in this LeaveHomeSafe application that was kind of mandated in Hong Kong was the SD card, right? In mobile applications, the SD card is what I like to call the Wild West of Android, because basically the SD card in many phones, you can extract it physically, plug it to the computer, and read everything, right? Because there's no encryption, there's no permissions, there's basically nothing. And also, like other malicious applications on the same device, can also read whatever is on the SD cards, right? So this is especially true in older Android versions, but the extraction of the SD card and plugging it to a computer is pretty much, like fully applicable, right? In pretty much all Android versions and Android devices with cards that can be physically extracted, right? So basically, even an unskilled thief can extract the SD card and plug it to a computer to read all the data, and malicious apps can read or modify any data on the SD card. Bottom line, you should not have like anything like too sensitive on the SD card. In this case, we found the LeaveHomeSafe application was storing the COVID-19, vaccination records on the SD card. So there was an option when you imported the vaccination records to import it, and you could import it, for example, from a secure location such as Google Drive, which requires authentication and maybe even second factor, right? So you go into your Google Drive and you upload a picture, and then this picture was being saved in the SD card, right? So anybody could extract your SD card from your Android device and see your vaccination record without any authentication, without knowing your unlock pattern on your Android device or anything else, right? So this was bad. So the way to mitigate this would be to avoid storing like sensitive data on the SD card, favor locations such as data, where Android can enforce permissions. And if necessary, you could have like a file provider that grants access to relevant apps like the Android camera on a, need to know, need to use basis, right? So this would be the main recommendations. And then if you really have to use the SD card, then you could try using encryption, then deleting things from the SD card after use, and stuff like that, right? But even threading would be not entirely safe because of flash storage. It's like threading. Like threading is when you like overwrite with garbage and lots of like different writes just to try to prevent forensic recovery. But even this is like not very reliable on flash storage. So the better solution, if you really need to use the SD card, would be to encrypt it first, and then there would be no problem with like forensic recovery or anything, right? This would be some of the ideas for mitigation. And then another thing we found was the COVID-19 like status access bypass, right? So there was an authentication bypass. I really like this issue because it's an issue that would be missed by every automated tool. And at the same time, is an attack that even your grandfather or your grandmother could do without any like technical skills. So basically, let me just come to the demo. I think I have a demo for this. Yes. So basically, what you're doing, right, is you're going to the settings and then you enable the authentication for accessing the vaccination record. So then, when you navigate to the vaccination record, it's prompting you for the Touch ID, right? Or in Android, it was prompting you for the fingerprint, right? So you should not be able to see this vaccination record, right? However, so you close the app, you open again, you try to access the vaccination record, and you see it requires Touch ID. However, you can just close the app, right? And then you go to the settings, and then you can see, well, first, I'm just trying again here to see if Touch ID is required, which is this. And then we go to the settings, application settings, and we just disable the authentication for accessing the electronic vaccination record. And now you can access the vaccination record without the fingerprint, right? So that is basically, the attack is basically very simple. It's like a logic flaw, right? And this happens a lot of times when applications require a PIN or something like that. You can sometimes launch an Android activity and then you bypass this prompt, or you can like go into the settings and disable it and so on, right? So how would you mitigate this, right? So to mitigate this, you would have to require the fingerprint again, you know, when, like before disabling the fingerprint, you should require the fingerprint again, right? That would be, you know, the better solution, right? And then another thing you could do is like require the fingerprint even to open the application, right? That would be even better because then you're protecting the whole thing, right? So, and then another thing in the LeaveHomeSafe application, right? This was like really bad. So it was so bad, I gave a talk about it. Was that you could man in the middle traffic without warnings using invalid TLS certificate, right? So let me see. Okay. So basically, the way this attack works is you would need to have some sort of man in the middle. Now you can even achieve this using DNS rebinding. So you could have like a DNS server that replies with the target domain constantly in the background really fast. And then you would redirect traffic to an IP you control, right? And then you need some domain on the internet. The name of the domain doesn't matter. The only thing that matters is that your certificate needs to be signed by a trusted certification authority trusted by the device. For example, you could register attacker.com and get a free certificate from Let's Encrypt, right? So these are all the attack requirements, right? You either man in the middle in public Wi-Fi or with DNS rebinding. So this would be the two most common. And then for my more like high profile adversaries, you could even like BTP hijacking or ASP man in the middle, but this is normally not possible for the average attacker, but DNS rebinding and public Wi-Fi would be easier, right? So let's break down this attack to see how it works, right? So we could intercept the logging, gain access to the login credentials, get the one-time password, and even intercept user-reported COVID infections. So the way to test this is, for example, if you're using Burp, you would trust your certificate on Android, right? And Burp would be the certification authority. And then the proxy server is configured to use 70security.com or attacker.com or whatever you want uh, for all the certificates, regardless of the inbound host header, right? Basically, if you try to access Google, I'm showing you a certificate for 70security.com. If you try to access Facebook, I'm giving you 70security.com, right? The certificate is only valid for 70security.com, but not any other domain, right? And then the way to verify this setup would be to open the Android browser, for example, and see if the Android browser gives you security warnings, right? Which it should, right? So the way you would configure it in Burp is you go to the certificate tab, and then you go to generate CA certificate, sign with a specific host name. So in this case, we're using 7security.com, but it could be attacker.com or whatever.com. This doesn't really matter. What matters is it's some domain signed by the certification authority, right? And then this should be rejected. And when you try to open like the LeaveHomeSafe URL that we are trying to man in the middle, right? You open this in the Android browser, you can see the Android browser is correctly showing a security warning, right? This is working as intended. There's no like security problem here or anything. This is, you know, what we were expecting. But in the LeaveHomeSafe application, there was absolutely no warning whatsoever, right? So you could like enter the username, the login, and everything. And when you log in, you could intercept all this traffic. You can see the username, the password, and other information. You can also get access to the PIN number, to the COVID infections, and so on, right? So we could intercept all this traffic. And the reason why it worked was that the hostname verifier part of SSL validation had this code in here, right? So string contains is usually bad enough on its own, right? Normally it leads to lots of security problems. Normally when developers try to do string contains, they really mean the string starts with or ends with. So when it contains, you can, for example, if it's a URL, you can add like question mark and the string they're looking for, and then that would bypass it. But in this case, what this is doing is saying like, if the domain I'm connecting to is one of these very important domains where Hong Kong people are trying to access the health system, then skip the hostname verification of SSL, right? This is very bad because basically, it's like bypassing the SSL verification from Android, which would be this one here, right? So they are overriding that and just returning true here without any sort of validation. Probably they added this because they had some sort of fake certificate in development or something. And then another conspiracy theories are that maybe they did this on purpose so it would look sloppy. So there's like plausible deniability that maybe they didn't want to do it while they were really, sending all the traffic to mainline China and then, money in the middling everything from there, right? So now that would be speculative. We don't really know, but the security problem is there. So um, cool. So with that, let me see if okay. So so there's a demo about this on YouTube, but I'm going to skip it because we have a lot more to go. So the way to fix this would be to improve the TLS validation and just use the TLS validation in Android to solve the issue. And then you can take this even further and use the OWASP pinning cheat sheet, which has examples for Android and iOS to improve the TLS even more, the TLS validation. And then what you do is you keep a hash of the certificate of the server that you are trying to connect to. And then if it doesn't match, then you refuse the connection. So even an attacker able to craft certificate trusted by Android will not be able to man in the middle, right? There's like lots of countries that can do this, as well as some companies like Trustwave, Google, and so on that could issue like a valid certificate for Facebook or any other domain they want, right? So with the pinning, what you do is you would provide protection even against that. And then an interesting solution that I found to the subsequent problem that happens when you implement pinning is that what happens if the user doesn't use the application in a long time and I don't update the fingerprint. So in those cases, I've seen a very elegant solution, which would be you would prompt the user to say, hey, I cannot connect to the server, try to update the application. And then the user goes to either Google Play or the iOS App Store and updates the app and gets the new fingerprint from there. And then you connect to your server safely, right? So this would be like the strongest form of SSL validation possible. Okay, another one would be man in the middle of clear text traffic. In this case, we're showing clear text man in the middle of MQTT, which is a protocol for kind of like sort of infrastructure or like IoT like, right? So to manage, it's normally used for like when you have like some sort of, IoT stuff in a factory and stuff like that, right? It was found on Bridge5. Now the reports are all public and all it's here, so I cannot like delve too much into this because we have many more slides to go through. But basically, uh, if there's no SSL, right? If you're just using MQTT in clear text, anybody can man in the middle the traffic, and anything that goes through the wire, we would be able to see. So you could, for example, do the traffic capture itself from the Android device. So you could do like TCP dump and generate some traffic. And then looking at the PCAP, we could see like we can intercept the traffic, and then there's some base64 encoded stuff that we can decode and basically read, right? So we can base64 decode JWT token sent over clear text, so we can see the name of the user, the email, the phone number, the password, and other stuff, right? So everything that is in the, you know, everything that goes through the traffic we can see. So clear text is bad, is basically prevented by default in Android and iOS nowadays, but it's very common for developers to disable this protection, right? We could also access MQTT messages sent between users. So one user in this application could send a message to another, and we could also see who was the sender name, the receiver name, and so on, as well as the message, right? So the root cause was that they were using MQTT like this. Now, this is true for any protocol, right? It could also happen with XML, XMPP, or any other protocol, even in email, it could be in an email application, right? Like POP3 or something like that, right? Now, all those protocols can be tunneled through SSL, but in this case, it wasn't, right? You can see enable SSL is set to false. So that would be actually like the way to fix it, right? Like setting this to true. And yeah, this is basically why it worked. You will also notice problems like this because the application will have to defeat the default protections, right? In Android and iOS version 9, in both cases it's version 9, they introduced like blocking clear text by default. So the developers have to go, in the case of Android, in the Android manifest.xml, and in the case of iOS, to the info plist. And in here, there should be some exception to allow this clear text traffic that the platform will otherwise block, right? So you can see allows arbitrary loads except to true, and so on, right? And then in Android, this is how the connection was being done, right? So you can see it's using a WebSocket, but it's using clear text as well. And also, like in Android, in the Android manifest, as I was saying, clear text is being enabled, right? So that is the problem. So the way to fix this issue, as well as to protect any protocol that doesn't support SSL, would be just to tunnel it through SSL. You should use like SSL, which is going to provide like the confidentiality and the integrity protections of SSL or TLS, right? Whereas the old protocol, in this case MQTT, is being tunneled through, right? And then you should also like disable all those exceptions in both Android and iOS, and that will ensure that the platform protections to reject clear text traffic are being respected, and therefore there are no leaks possible, right? Okay, so now we finished some of the Android examples. Of course, there's many more. You can see the public reports for that. And I'm just going to show like a couple of interesting web attacks, right? So this was an arbitrary account takeover using a mix of an insecure direct object reference that could also be considered an HTTP parameter pollution, right? So this was found on the WebPN backend. And basically what we are doing here is we create two accounts, one for the attacker and one for the victim. And then when you log in as the attacker, right, this is using like the normal login flow of the application, we get an access token. And then we can verify that the token belongs to the attacker account. So we can see our own profile using this like attacker token. We can see this belongs to the attacker. Until here, there's still no attack. This is just like the preparation steps. And then now this is the attack, right? This is the cool part. So here you can see we have an attacker ID, right? A victim ID, which is different, right? So this would be kind of the insecure direct object reference part. And then we're using the attacker authentication, right? So we logged in as the attacker in the previous step. And here we are setting a variable for the attacker authentication, right? So this is going to be sent to the API like this, right? So the trick we are using here is that, especially in Python, right? But this can also happen in other platforms. In Python, it's very common to use the user ID in the URL for access control. So normally there's some sort of a routing mechanism that is going to check if the user logged in is user A and the user ID in the URL is user A, then grant access because everything looks okay, right? So what we are doing here is we are seemingly trying to update our own profile, right? So we are logged in as the attacker, and we are trying to update our profile, so this looks legit. However, the trick we are doing here is in the post body of the HTTP request, right? So this B is for like data of the post body in the HTTP request. We are setting the ID to the victim ID, right? So what's happening here, right? By having the attacker ID, we are bypassing the access control text. Whereas when the final endpoint retrieves the data from the post request, it's taking the ID for the victim, which is a different user, right? The victim user. And then normally, like in most frameworks, post is going to have more preference over more precedent over get. So this victim ID is going to override the attacker ID. So what we are doing here is we are changing the email address of a victim user to an email address that we control. So now after doing this, we can see like the victim ID, right, not the attacker ID, has been modified, and the email is an email address that we control, right? So then after that, we can use the forgot password functionality, and we can reset the password to any password we want, so we can take over the account, right? So we are resetting the password, and now we can log in as the victim user, and now we have access to everything that this user has had access to, right? So it's a very cool attack. Um, and the reason was that the ID was being retrieved from the post body, whereas the ID in the URL was being used for validating the access control, right? So this is a very cool attack vector that you should always like try, because sometimes it will give you results, especially against Python applications, but in other frameworks as well, right? These would be some recommendations, right? So you should like verify like users are updating their own stuff and so on. And then another cool attack from another audit was this arbitrary access using crafted JWT tokens. We found this problem in Litmus Chaos. Now the audit is all public, right? So the reason was that the secret key for JWT tokens was publicly exposed, so we can create like any valid token we want. So we can create a token at admin, for example, right? We create our Python script, and then we can generate a valid token to log in as admin, and then we can become admin basically. Now this was really bad because Linux Chaos is an open source software, so this hard-coded JWT token was public, right, for anybody in the planet to see. So anybody basically could do this, right? So this is why it was bad, right? So this is why the problem happened. Is basically they had this hard-coded secret, and the project is open source, right? So then anybody can see it and craft any JWT token that they want and log in as whoever they want in the system accordingly, right? So you should not have like secrets hard-coded in your applications. And then using environment variables is an improvement, but even better would be to use like AWS, Secret Manager, and so on, right? That's those are some ideas. Then another interesting example was this gRPC bomb. This was against OpenTelemetry. And then in this case, this was a very interesting denial of service, because what we are doing is we are creating a zip bomb, but in an HTTP request, right? So OpenTelemetry had like different types of supported compression algorithms. And then what you're trying to do as an attacker for denial of service is anything that creates a lot of asymmetry, right? Like you send a very small request that then on the server is going to result on a lot of work, right? Or a lot of memory usage or something like that, right? So what we are doing here is we're using this Python script to create a zip file that for the attacker is very small, right? It's like a very small file because it's an empty zip file, but when uncompressed, this is going to be 10 gigabytes, right? So when the server receives this request and uncompresses it in memory, it's going to use 10 gigabytes of memory, right? So, so we basically create this like zip bomb using this compression algorithm, and then we are sending it with curl, and you can see here that this is basically failing, right? So let me see if I can hide this somehow, move it down, or yeah. Okay, so I'll just put it there. So you can basically see here that there's like a failure when receiving data from the peer, and all these reports, the public report relevant to the finding is at the bottom of the page as well, if you want to read more about any of these findings, right? Yeah, and this is like the crash on the server side with the logs, right? You can see like it exited and so on. And then this was the problem, right? It's like trying to decompress the input without, having any sort of like validation, like, hey, this is like taking too much memory or whatever, right? So now this is tricky to fix, right? Because like you have compression for a reason to try to make things fast and so on. But of course, if you disable decompression, you would immediately solve the problem. And then another possible mitigation would be to limit the decompressed data size, right? So you should have like have like a reader that reads like one step at a time, like the decompressed stuff. And as soon as you notice like, hey, this is like taking too much RAM or whatever, you just stop it without crashing the entire application, right? So this would help prevent excessive memory usage and would protect against the out of memory errors and so on. So other things would be like single packet denial of service using a spoofed UDP handshake response. In this case, this is critical because it was an application meant to provide like internet freedom. So a government such as Russia, China, Iran, and so on can just send this packet and then the entire solution stops working, right? So this was found on mini VPN, and you can read more about it in the report, but this is basically how it works, right? You would run the script from the terminal, and then you would start the client in another screen, and then what you do is you send a malformed UDP packet during the VPN handshake process, and then would basically like crash the application, right? So this is how the attack looked like. You're basically like sending a malformed UDP packet, and then UDP can also be spoofed, right? It's not like TCP where you have like the three-way handshake at the beginning. With UDP, you can send a UDP packet, even like faking it like it's coming from a different IP address, and it will still work, right? So the UDP is very interesting for these types of attacks when supported, right? And this was basically like crashing the application, right? It cannot complete the SOC 5 connection, um, and that's it, right? So basically, the VPN client cannot connect to the server, and therefore this is very bad because it assumed like users are trying to use this VPN to protect themselves from an oppressive regime type of government. So yeah, the VPN handshake would fail and so on, right? And this is how it looked in Wireshark. So, so yeah, so this is how the proof of concept was built, how we were like creating this like bad packet, and then um, you know this would be like how to fix this problem. So let's jump into the cloud vulnerabilities. So we have a little bit of time to cover those. So in cloud stuff, sometimes there's like some credentials or something that can be like assumed by some of the trusted roles with excessive privileges, and then you can become like infrastructure admin or something like that, right? So this is a problem like we see very often. So in this case, several of the AWS accounts that we audited failed to have like the strictly minimum necessary permissions. And this was a problem because all accounts had kind of administrative privileges, right? Because of this like propagation of privileges. So you could like assume a certain role and then become admin, right? So it was kind of the problem. And this happens very often, right? So this was like the proof of concept, like we could see like all users and administrators. You can navigate to the administrators group and you could see like all users and administrators. Then you can use like a trust relationship, um, to see that, the users would be able to, you know, using the permission propagation, like basically gain access, right? So you can see like allow is set to star, right? So you can basically using the trust relationship exploit this, right? So this is the trust relationship which grants full privileges, right? And then the way to mitigate this type of problems is very tricky, right? But you should try to apply the principle of least privilege, right? So giving users as few permissions as possible so they cannot do stuff like this, right? And then prevent users and automated tools from having excessive rights. And then you can use some tools such as CloudWatch or IAM Analyzer to help you with those things to generate policies based on the access activity and so on, right? This was one of the issues. And then, yeah, I'm not sure. Okay, maybe I have enough time to do the prototype pollution. So let me see um, if that works. So let me try because I thought we wouldn't have time, but apparently we do have time. So give me a second. And what I'm going to do is try to start this VM and we will see if um, if this works. So I'll explain it. I'll explain like prototype pollution as we go. So, so this is a very interesting case where we are using prototype pollution, but on the client side. And then what we're doing is we are messing with one of the function definitions that the application has, right? You can use prototype pollution and exploit it on the server side, but in this case, we're doing it on the client side against an Electron application, right? This is based on a real attack against a real application, but the application is kind of a dummy, right, to illustrate. So let's see if I can make this work. Let me see if this was already opened or not. Yeah, I think it wasn't. So cool. Okay, so let's see how this works, right? So the first thing is to send a user a message, right? Um, so you said you have a victim user, right, and an attacker user. In this case, I'm sending a message to myself, which is very sad, but it's just to illustrate the point. So you send an attacker sends you a message, right? And then you click on this, and then the application says like this link is unsafe, right? Because it is, right? If you open a file URL with a Java extension, it will be code execution without warnings, right? So then the reason this works is because of this check here, right? It's doing this link is unsafe whenever there's like a click, and then it's reviewing the links, and then it's checking if the protocol of the link is safe, right? And a safe protocol in this case would be HTTP or HTTPS because it will be opened by the browser in the operating system, in this case Windows, but it will be the same on Linux or Mac, right? So in general, in Electron applications, an HTTP or an HTTPS URL is safe because the browser will open it, but a file URL is more dangerous because an application could open it, right? In this case, it's going to be the Java application giving us remote code execution, right? So then what we want to do is to mess with it, right? So if we break down the logic, we go here in the developer tools, you can say like it's a safe protocol, right? And then the index of function of HTTP is going to return 0, right? And if I do HTTPS, also is 1, right? So this is position 0 of the array, this is position 1 of the array. But if I put here anything else, right? If I put here file or whatever, it's going to be -1, which is unsafe, right? This is what we are trying to bypass here, right? So the way to bypass this would be like, you do this, right? So I'm clearing this, and then I'm sending this message like, hey, look at this. And now using XSS, we are creating a broken image, right? Where we are using the on-error event to redefine the index of function to return lead. And now lead is always going to be different than -1, right? Which is the logic here that, like this safe protocol index of is different than -1, then it's considered to be safe, right? So now if I do index of HTTP, so if I do file, it's also going to be lead. If I do HTTP, HTTPS, or if I do file, right, all the links are going to be lead. So this means that now when I click on this, we are no longer getting the warning, and instead we are executing this Java file, which in a real attack would be like file attacker.com electron or ce.jar. And then because Windows will fall back into WebDAV, you can have your WebDAV server on the internet with this like Java file, and then you have full-blown remote code execution, right? So yeah, so with this, this is like the end of the presentation. And with that, I believe we have some time for questions. Something I'll mention briefly is that every year we have a free pentest contest. So if you know anybody that needs a pentest and doesn't have too much money or whatever, they can participate here. This is all completely free, no strings attached. You get like a full pentest. We also have free workshops. So there's a 4-hour workshop about practical mobile app attacks by example, 1 hour and a half for deep links and accesses against Android and iOS. There's also 1 hour about web security, and I think 1 hour and a half for electron security, which is a little bit related to what I mentioned before. And then if anybody is interested in a pentest but cannot wait for the contest, we also have like a discount code here and another discount code for anybody potentially interested in for security courses. You can use this on a training store, or you can use this to, have $1,000 off of a pentest or 40% off any security course. And with that, feel free to ask any questions.
Thank you, Abraham. We have few questions. I'll just read out that for you. How important is the SSL chain?
Well, the SSL chain is very important, but as I mentioned before, the problem is the trust, right? So the SSL chain is generally very important because like Android and iOS are going to trust like a number of certification authorities in the world. In theory, it's very well secured and so on. In practice, we have seen over the years that sometimes some certification authorities, notably DDNotar, were hacked, and then hackers were able to craft certificates against Google, Facebook, and many other domains. So the TLS chain provides a lot of protection, but even better protection would be to implement this pinning approach that I suggested before to improve the SSL validation. Because when you implement pinning, then you're bypassing all the trust mechanism, and you are only trusting the fingerprints of servers that you trust. That your mobile application has this hash, and then if it doesn't match, it's going to refuse it. So even if a certification authority is hacked, let's say Trustwave or any other certification authority gets hacked, right? And then attackers now suddenly can start creating certificates. Those applications implementing pinning will still be protected or protecting their users against this form of man in the middle. Now, nowadays, I believe like certification authority hacks have been less common. Implementing the normal like TLS validation is already like really good protection, but implementing pinning would make it like even better, right? Like even some certification authority gets compromised, you're still protecting your users from this type of attack.
Thank you, Abram. Meanwhile, I'll take up the next question. I would request in the audience, if you have any questions for the speaker, please write them in the Q&A box so that we can address those questions. So, Abram, next question is, would you like to share some best practices for hybrid, that is on-premise plus cloud deployment?
Okay, this is like a very broad question, and it's kind of, difficult to answer it like in a minute, but some of the best recommendation I can provide would be to look at the OWASP cloud security guidelines as well as the CIS benchmarks. And these details, like all the, professional like standard practices for cloud security, right? Because we don't have time like to go through everything in detail, like in a minute. But in those resources, like if you do your best with that type of stuff, you would be like in a very good place. And then in general, one of the most important things would be the least privilege, right? Now this is true for security much more broadly than just cloud, right? If you have employees, your employees should only be able to access what they are supposed to access to do their job. In the cloud, it's the same, right? If some employees are supposed to have access to one server, they should not be able to access the other servers, and so on, right? So you would need to set the permissions, right, as strict as you can. Or for example, like this server should only connect to that other server and not to the internet or something like that, right? That's also like a very common problem that we find in security audits, that the servers that they don't need the internet for anything for what they are doing, but they are still able to connect to the internet and there's no filter whatsoever, right? So if the host is somehow compromised, then an attacker would be able to extract everything and send it to the internet, right? So you can implement, as little privileges as you can, and try to control the network flows as hard as you can, like with firewalls and so on. So servers are only able to connect to what they are supposed to connect to do their function, and people can only access the resources that they are supposed to access and nothing else, right? Now, this is very easy to say and very hard to do, because in practice, especially when companies are very small, it's pretty common to have like a developer that has like full access to all the servers and stuff like that. But as you mature, you should try, to implement as many of these restrictions as possible, and ideally, like require different people, right? There's another security principle that is the separation of duties, right? So, for example, release into production, you could have like a developer has to commit the code, but then to push this code into production, there's like some sort of a code review and so on that needs to happen, and an administrator or somebody else needs to approve the release before it goes into production, right? So even if you have like a malicious employee trying to, release like a vulnerability